When most developers start building with generative AI, it looks like this: a chaotic, unstructured stream of raw API calls hitting a single endpoint. But at an enterprise scale, system architecture has to look completely different. It must be highly ordered, methodically routed, and perfectly deterministic. Getting a basic prototype working with Claude takes an afternoon, but taking that fragile single-turn script and deploying it reliably into production without compute costs spiraling or latency spiking is a massive infrastructure challenge. That's why scaling requires an enterprise environment like Google Cloud's Vertex AI. It provides the secure foundation and precise architectural control needed to surround the model with strict engineering safeguards. Scaling to production involves integrating the large language model as a standard computational node within a larger, governed software system. This means explicitly building the components that sit around the model: automated prompt evaluation loops, multi-index retrieval pipelines, contextual caching layers, and standardized integration protocols. The core philosophy of this build is straightforward. We are discarding intuition and replacing it with engineered determinism. Achieving production-grade reliability involves moving beyond simple prompt adjustments to address the complexities of predictable routing, state management, and integration standards. This diagram starts with a central node, Claude on Vertex AI, receiving a linear flow of raw text. Our first principle of control is the system prompt filter. It stops conversational responses, forcing the model to return uniform, rigid blocks of structured data. This schematic shows a JSON data structure defining specific key-value pairs. By enforcing this exact layout, we lock Claude into a predictable behavioral contract. Downstream applications will always receive a precise formatting they require to parse the information. In production, we must build an automated prompt evaluation loop. We evaluate outputs systematically, replacing intuition with testing. This happens on two tracks: deterministic, code-based grading, and a secondary AI node to grade the primary model's output. We generate massive test datasets to continuously push data through this dual-track loop, constantly measuring the performance of our system prompts under high volume. A rigorous pipeline mathematically proves a prompt's real efficacy. This is the only way to test before exposing it to the chaos of real-world scale. With the foundation secured, we face the primary bottleneck of any enterprise deployment: context limits. This occurs when passing massive payloads, like complex images or 100-page PDFs, to the model repeatedly. If Claude processes that dense manual from scratch every time, latency degrades and compute costs multiply. We fix this by inserting a prompt caching layer. Instead of rereading the entire file, the system stores repetitive data in a high-speed buffer, passing a lightweight reference link to Claude. A timer clears unreferenced context. Prompt caching is the essential architectural requirement that suddenly makes massive, enterprise-scale document analysis economically viable and incredibly fast for real-world deployments. Even with caching, a base language model is inherently static. Its training cuts off. To provide accurate answers about your private organization, it requires a pipeline to dynamic external knowledge. In the RAC pipeline, raw external documents are sliced into uniform chunks and enter a multi-index search. The top path uses BM25 lexical search for exact keyword matches. The bottom path uses vector embeddings, translating text into mathematical coordinates to capture semantic meaning. The pipeline merges exact keyword hits with conceptual vector matches into a single stream. This merged stream hits a re-ranking node, which mathematically scores and dynamically pushes the most critical chunks to the front. The final safeguard in this data flow is contextual retrieval. The system appends a brief, automated summary of the larger document to every chunk. A multi-index RAG system guarantees that the model's responses are anchored exclusively in verifiable, retrieved organizational truth, neutralizing the risk of hallucination. While retrieval provides the model with context, executing real-world actions requires Claude to interface with external tools through explicit functional definitions. This visualization shows a tool schema. It's an explicit contract defining a specific external function, the parameters it accepts, and the exact required data types. Claude is bound by this schema to execute the tool correctly. Executing tools requires managing recursive message blocks. Claude will output a request, pause computation, wait for the external function, and then ingest the resulting data to resume. Historically, developers had to write custom, hard-coded integration scripts for every single database or API the model needed to access. To solve this, we introduced the Model Context Protocol, or MCP. It replaces tangled custom code with a standardized protocol layer. This protocol splits into two interlocking halves, a client on the Vertex side and a server attached to the external resources. Through this secure, standardized handshake, Claude gains immediate, frictionless access to web search, text editing, and deep environment inspection without any custom scripts. Standardizing integrations through MCP eliminates technical debt. It turns a fragmented mass of APIs into a secure, plug-and-play ecosystem for AI tools. Giving a model tools often leads developers to build fully autonomous agents, giving the AI a goal and letting it loop infinitely. But unbounded loops fail predictably. Reliable AI architecture relies on explicitly routed, deterministic workflow orchestration. We establish this control using distinct workflow topologies. The first is parallelization, splitting queries into simultaneous pipelines. The second is chaining, where sequential logic locks the model into a defined path. The third is routing, where a central node conditionally switches tracks to specialized prompts. Standardizing these workflow topologies creates the guardrails for a predictable software application, effectively removing the volatility inherent in unconstrained AI loops. This diagram represents our complete production blueprint on Vertex AI. We replaced naive connections with engineered determinism, installing automated evaluation loops and high-speed prompt caching. We grounded the model via a multi-index RAG pipeline and standardized external actions with the Model Context Protocol. Google Cloud's Vertex AI provides the secure, scalable compute environment required for the system to run. But it is the architecture we wrapped around it that provides the determinism. Organizations skipping these foundational layers, treating the LLMs simply as a chatbot, hit insurmountable barriers of latency, cost, and hallucination when trying to scale. True mastery of Claude requires treating the large language model not as a standalone oracle, but as a single, powerful computational component within a rigorously engineered deterministic pipeline.